Okay, hello everyone. Let's start today's session. Uh, so far in this course, we learn how to basically model the system, both in S-domain and time domain. We learn how to find the time response of a system. We learn how we can determine the stability of the system. We talked about that. We kind of like introduced the concept of that plotting the poles and zeros in the Cartesian kind of like uh, system. And we talked about that, okay, if we have like a poles, the poles are the one that define the stability. Now, if we have a poles in the right-hand side of that plot, then we have problem. We have uh, instability because we are gonna face some exponential increase in our output. And if we have all the poles at the negative or like left side of the uh, plot, then we are good because all we have gonna be multiplied by an exponential decay, which meaning we are gonna end up with a finite steady state response, meaning we have a stability we can control. And we already also talked about the marginal stability, which was when we have poles on the, we only have poles on the y-axis or imaginary axis. Uh, and we find out that that actually means the oscillation and a sustainable oscillation. But since that oscillation is sine and cosine, and we know that if we don't have a exponential with a positive uh, power, okay, then we don't have a problem. Although we have oscillation and we don't have a solid steady state value, but still we are between an interval of a maximum and minimum. The system is oscillating between those, so still we are marginally good to control the system. Now, everything that so far we discussed, we consider the system as a static system. So every component that we had was solid. Like the second order system, that RLC system that we talked about, the resistor was constant. It wouldn't change through the time. The inductor was constant. The capacitor was constant. That means the natural frequency of that second order remains as a certain value through the time, same as the damping coefficients and damping ratio that we described. So everything is static. Now we are going to move toward the system that one or multiple components, okay, or properties or variables in our system are changing. Okay, those parameters are now dynamic. So through the time, they might change. One example would be the system, the control system that help you to actually manage the temperature of the room. Okay, so we have a measurement of the temperature. Very good. Then we are going to have a certain electrical circuit, the control circuit, that is going to manage the either like the this is a specific control system that we designed. Like the most famous one is like a PI or PID control system. Okay, but what is important in reality when we use like resistor or inductor or capacitor or even transistors in digital design, or like this is like an analog design actually, the transistors in like a processors or amplifiers, okay, every single one of them are sensitive to the temperature. So it's not that you have a solid control system that controls the temperature. When the temperature changes, the characteristic of that system would change with the temperature. Okay? Now, that being said, that means the alpha that, for example, the second order system, which is pretty much the PID controller, okay? The alpha, that decay ratio that we described, okay, would change, same as omega n. And we said the relation between the two would actually give us what type of response our system is going to have at the output, okay? What that means? That means the poles of the system are changing. Is that clear? So we are going to have some system that through the time, for any type of reason, the parameters are changing. That means the poles are changing or moving in that Cartesian system, okay? Now, this is one aspect that we can introduce a dynamic system, okay, or dynamic transfer function. Another one is when you want to dynamically change your control over system. Like for example, at a certain time, you want a decaying coefficient of equal to A, but later on you want to increase the decay, okay? So you want to increase the decay coefficients, okay? What that means? That means you want something to be dynamic, so you are able to change that parameters. But if we have that, then we don't have a solid transfer function. What that means? That means the stability analysis that we are doing for in a certain specific system is not going to be valid when in future we are going to changing some parameters and we are going to have a different system. But it's not actually logically efficient to constantly run a stability analysis. Does that make sense? So what we can do? What we can do is to introduce the dynamic transfer function when the poles of the system would move around in that graph. Okay, and try to analyze that. Okay, try to analyze that based on that dynamic poles. When we want to do that, now another techniques or concept comes into the play, which we call it the root Locus techniques. Okay, so we are going to have another techniques named root Locus, okay, which basically help us to analyze what's going to happen if we have the dynamic poles, the changing poles. Okay, now the root Locus basically is a graphical representation of our system when that system is closed loop. So we are not talking about a simple transfer function. We are going to talk about a closed loop system, that feedback situation. When we have a closed loop, so we have our input, we have our, for example, g of s, okay? And then we have our feedback that could also have a certain h, okay? And we know that if we have such a system, what would be the transfer function of the whole system? We already talked about that. If we have a feedback and it's a negative feedback, now the transfer function of the system is not just g and h. Basically, the transfer function becomes forward pass divided by 1. Now we have negative feedback. So at that, we basically call it feedback. Okay, if you have positive, we call it feed forward. Okay, so 1 plus h of s, g of s. Do you remember that? That was how we drive the system transfer function when we have a feedback. Now, we said we wanted to like introduce a dynamic situation. What that means? That means, like for example, we can introduce a gain. If we introduce for example, a gain here, let's say K, okay, we consider the gain as a variable parameter. It's unknown value that either we have to consider the variation in it, or we actually try to set that, tune that value and use it for changing the control system. Okay. Now, if we have such a system, okay, which K is the gain added to that system, our transfer function would change. The new transfer function would change simply to K G of S, okay, and the denominator become K H of S G of S. Now, you can easily see that when we talked about the stability, we said what we care about is the poles of our transfer function, which is the zeros of the denominator. Now, it's already can be seen that if we have a K that is variable or changing, then we don't have a solid poles. Make sense? Because if we put that equal to 0, now this K would get into the values of the poles. So by changing a K, the place of our poles is also changing. Are we good? So this is basically the very simple description of what Root-Lucas technique would actually try to do for analyzing the stability of a dynamic system and see what's happened by the change of, like, for example, a variable. It could be a K, which is a gain, or even we could have a K inside the G, inside the, like a feed-forward transfer function or feedback transfer function. Okay, does that make sense? Now, that being said, I wanted to try to introduce another concept, because that would help us to represent the poles in a easier or like most kind of like understandable way. Okay, are you good? I wanted to like raise the word. Are you good? Right. Now, we said that when we wanted to show the roots and zeros, let's say this is an example of roots and poles, basically zeros and poles, we can use the graph and we can place the poles in a real imaginary system. So this is the imaginary axis, this is the real axis. Now, when we wanted to describe like this pole, like this specific pole, how we would describe that? We said that if this is imaginary and this is the real part, we have a complex number that would show us what is the value of these poles. Okay, so for example, these poles could be like a alpha plus j beta. And we already know about the symmetry, so this one, for example, is going to be alpha minus j beta. We showed this by showing a complex number. Okay, now you can imagine these gonna be like, for example, like lambda, gamma, or omega. These are the values, the simple value. On the x-axis, we have just the real numbers, but on the imaginary or the complex part of our system, we are gonna have a complex number. This is one way to show those zeros and poles. Now, I don't know if you remember, you should be introduced to this concept earlier in the courses that you passed, but we also have another way to represent our system, which is the phasor kind of like a representation. Now, the phasor basically means that we can show any complex number or any number. So that imaginary part could be zero, but we still can represent that like beta or that like that y alpha. Let's say this is gamma. We can show that gamma equal to the gamma plus j times 0. Okay, it's a still complex number, just the imaginary part is 0. Okay, now the phasor representation of this complex number is basically means we can represent this number as a vector that initiate from the reference that we have. It could be, the reference could be the 0 of our graph, our system, okay? Or it could be, you can move that 0, it doesn't matter because you're just shifting the vector, okay? And for example, we can represent this complex number with a vector. I'm going to initiate from the 0, okay, that had a certain amplitude or magnitude, okay, and have a certain angle with the real axis. Are we good? And has a certain angle with the real axis. This is our vector. We show vectors by magnitude, and angle, which that angle actually represents the direction of that vector. So I can show this complex number with a magnitude and an angle, which we call it phase. Is that clear? I assume you are familiar with the phasor, right? Okay. Now, and we basically know when we have a phasor, that magnitude is simply this is like a triangle. We can use the triangle relation, okay, and this is like a 90 degree. So we can use it and say, okay, this value here is beta, and this value here is alpha, okay? So the length of this vector is going to be the square root of alpha squared plus beta squared. Are we good? Now, what about this theta? This theta, again, we can use the triangular characteristics, which we know the beta is actually equal to that m times sine of that theta. Are we good? And the alpha is basically m times cosine of that theta. The projection of that vector in real axis and imaginary axis. Cosine, sine. Are we good?
It is also.
Sorry?
It's trying.
It's gonna be the same. It's gonna be the same. But you look at this. Look at this. The cosine of this theta, okay, is equal. This is the projection. Is equal to the cosine of this theta. Correct? Because it is still the projection that shows the same value. So as sine. And you probably already know that when you have a theta, 180 minus that theta in sine and cosine is going to be the same. Are we good? Now, so if this is sine and this is cosine, okay, times n, I can find that the tangent of that theta, the tangent of, let me use another color. The tangent of that theta is simply m sine of theta over m cosine of theta, right? So what is going to be theta? It is going to be the inverse tangent of, our nominator is same as beta, and our denominator is actually the alpha that we had before. Are you good? So this is the representation of our pole when we had before in a complex, as a complex number using a phasor representation, showing it with a vector. Okay? Now, when we talk about the stability, we want to see what would be the value of our S, what would be the value of, our of f of s or t of s, the function at a specific pole. Let's say I wanted to see if I have a pole here, the point here in my system. I want to see if I'm here and my s is equal to whatever value, like a plus jc. Okay, if I have such a value for this specific point, am I gonna have a stable system or unstable system first? And what I'm gonna have as a value, as a final value, okay, of my transfer function. So what I mean is I wanted to see, let's say, I want to see what is the value of my transfer function that is described by these zeros and poles, okay, when s is equal to that point, a plus jc. Okay, now, one thing that I can do is to simply, I have, like, for example, the transfer function, I can simply put the a plus jc as a s into my transfer function and solve it using the algebra. Are you good? Now, that's easy when you're talking about the first order, doable, like easily doable, a little bit challenging when you have like a second order system, okay? But like for such a system, you can see we have 1, 2, 3, 4 poles. So we are talking about the fourth order system. So now it's not that easy to actually directly solve the T of S, okay, using the algebra and putting just the value that we want in the transfer function. Now, one thing that this Locus property, one of the property or advantages that the root Locus technique has is we actually we can use the phasor representation of the relation between each of the poles and zeros in our graph, okay, refers phasor representation of each of the relation between each of the poles and zeros in our graph with that specific point and find out the value of TS. Now, let me show it by an example. Can I erase this? Yeah. Let me show it by an example. Let's say we have a transfer function that is, for example, s plus 1 times s plus 2, s plus 4, s plus 6, and I have another s2. Okay, this is not the transfer function of this plot. You already know that, right? Okay. Let me have another s, which is s2 plus 4. So it right now is 1, 2, 3, 4, 5, 6. 6 order system. If you want to put, for example, the point when alpha plus JC is, for example, is minus 3 plus like J 8. Okay. Now putting that number in the transfer function would give you a hell of a kind of like challenge to calculate the T on that point. Now, but look at this. Look at this system. We said that if we have a graph, okay, for this specific transfer function, we can draw and show the poles and zeros. How we can do that? The zero is s equal to minus 1. Okay, so let's actually do that. 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so one of my zero is on minus 1. So this is my zero, correct? One of the poles is at 0. I have another pole at minus 2, another one at minus 4, another one at minus 6, and another one, actually two poles at plus minus j. Is that clear? So I also have 2 poles at plus minus j. Now, the point that I wanted to like see what's going to happen if I put that point in TS is minus 3 plus j8. Let's actually show it. So this is 1, 2, 3 minus 3. 1, 2, 3, 4, 5, 6, 7, 8. So the point that we want to see is this point. Are we good? Now, we said that instead of complex number, I can show it by a phasor, by a vector. Right? So, if I have a vector that starts from the reference 0 to show that, let's say, this vector is m1 in a magnitude and theta 1 in a degree. Are we good? Now, for this specific component, that's 0. Okay? If I put this value inside this term, it means I'm shifting it 1 unit. Correct? Are we good? So if I'm shifting it 1 unit, it would become the real part. The imaginary part would not change. The real part would change 1 unit. So now it's minus 2 plus j8, and minus 2 is here. Okay, so this is gonna be the new vector if I put that number here. Correct? Now, this has, let's say, a value, the vector has m2 with a phase of theta 2. Are we good? Now, if you use the triangular system, you can see that this vector is actually the magnitude and the theta of this vector is actually equal to this vector. They're starting from 0 all the way to the point. Use a triangular way, you can find it. So this vector is also equal to m2 theta 2 degree. It's just a reference. We shift the reference. The vector didn't change, we just replace the reference. Okay? Now, with the same process, we can see that if we put the number in the first term of the denominator, same process, we can see that if the vector result is going to be the equal with the vector that we have from this pole to this point, which this one is like m3 theta 3. Are we good? Same goes for all the other terms in a denominator. So we are going to have m4 theta 4, m5 theta 5, So if I put this number here and change it to the phasor base, my value of T of S can be also calculated by the phasor representation of those values. So this one is going to be M1 theta 1. Okay? This term be represented by, what is that? This is M3, right? Oh, this is M2. Sorry. M3 theta 3. Then this one become M. I use this for the complex, so this one become M 4 theta 4 and M5 theta 5. Okay, so it's gonna be M4 theta 4, M5 theta 5. Then I have M6 theta 6. This one is M7 theta 7. And the last one, M8 theta 8. Right? Now, do you remember how to calculate the multiplication of phasors? When you have the multiplication of the two phasor, the result of that would be the multiplication of the magnitude. Remember that? The multiplication of the magnitude. So this is how you show the multiplication. Okay? This symbol is multiplication. Can you see that? Okay. Of M, let's say I, which I goes from 3, 1, 2, 3, 4, all the way to 8. So this is my M. Actually, no, let me don't do that because it might be negative. Okay? So that's my amplitude. What about the phase? When we have a multiplication of the phase, what would happen there? You add them together. So now it's become the summation of those thetas from 3 to 8. Are we good? Is that clear what we did? Now, what about the division? Now, in the denominator, we have this complex number and one complex number in a phasor domain, and we have another phasor in a denominator. So the division would be what? The division of those. So the T of S, when S is -3 plus J8, is going to be that M2 divided by that multiplication that we have. Okay, what about the theta? It's a subtraction, right? Numerator minus denominator. So it's going to be theta 2 minus that summation that we have. Are we good? Now, look at the formula and let's try to make a general formula for any transfer function. Okay? Now, the general formula we can write is the T of S when S is A plus JC, okay, can be shown by whatever we have here in a denominator, the multiplication. We can have several zeros. If we have several zeros here, we have the same situation here. So this could be also multiplication of them. Are we good? It's gonna be the multiplication of the amplitude, mi, I goes from 1 to, let me, mz, zeros, this is better, from the first zero to the m0 that we have, okay? This is a better way to show it. Is that clear? And the value in the denominator is again multiplication of all the magnitude of the poles, okay? When the poles goes from the first pole to, let's say it's the nth order, so all the way to the nth pole. So using that example, we find out that we can actually calculate the magnitude of our transfer function in a specific point, okay, using the magnitude of the vectors from the zero or zeros, connecting the zeros to that specific point that we want to see, okay, divided by the multiplication of the magnitude of the vectors that connects the poles to that specific point. Okay? Now, what about the phase angle? The phase angle, we know, is going to be the summation of the the theta's of the zeros, those vectors that connect the zeros, from the 0, 1, the first zero, all the way to the nth zero, minus the summation of the theta of the poles from 1 to n. Any question? So using the direct way to calculate the t of s on a specific point, we were able to actually develop a general formula for any type of transfer function. So now we don't need to actually run this crazy function on that complex number. Are we good? So you can see that one of the characteristics of our pole zero graph is that we can find the value of our t on any specific point in our graph. Are we good? Any questions? No? No. Let's see how these concepts are related. The root Locus concept and the phasor concept that we have for each point in our complex vector. Can I erase this? Right? Okay. How we can use that in order to find out what's going to happen to our transfer function and how our poles are changing will affect our stability of our transfer function. Now, let's use an example, okay, for a system that has a value in it. Now, I'm going to use the transfer function or a block diagram. Let's go for the block diagram. Minus plus. I'm going to have a gain of k and another transfer function that says k over s times s plus 10, and I'm going to give it a unity feedback. Are we good? Now, what's going to be the transfer function of this, the general transfer function of this whole system, the feedback system? We already said that. It's going to be the denominator divided by, it's a negative, 1 plus, this is a unity, so it's going to be 1 times the denominator. Are we good? So, if you run the math, I'm not going to do that. Our transfer function is going to be k over s squared plus 10s plus k. We have a second order, but now we have some unknown values in our transfer function, okay? That if it change, it would move our poles. Are we good? And we don't have any zeros because we have a constant number always. Now, let's see what's going to happen. The value, let's see if I have the value of the k. Well, we know how to write it. S1 and S2 were minus alpha, which is half of this value, minus 5, plus, you remember that, right? The square root of alpha square, which is 25, right? Minus omega n square, which is the square root of whatever we have here. So omega n square is going to be the same thing, so minus k. Are we good? We have plus minus. We have 2 zeros at these values. Alpha square minus omega n squared. This is omega n. Remember from the second order system, this is 2 alpha. This is omega n squared. And this is minus alpha plus alpha squared minus omega n squared. Plus minus, sorry. Okay, now you can easily see if I have, let me actually draw a table. I have 2 poles that are going to change. Let's say pole number 1 and pole number 2. And it would change based on whatever k we have. If the k is 0, what's going to happen to my first pole? If the k is 0, here, this becomes 5, right? So it's minus 5 plus 5 and minus 5 minus 5. So one of my poles is going to be minus 10, another one is going to be 0. If the k changes to 1, or let's say let's go for it. I wanted to be consistent because I have a calculation for this. If k is 5, then my pole would change to minus 9.47. You can do the math. and minus 0.53. If it's 10, it's going to be minus 8.87, minus 1.30. If it's 20, I'm going to have minus 7.24 and minus 2.76. And if it's 40, I'm going to have minus 5. Plus, now we are moving to the complex numbers. J 3.87 and minus 5 minus J 3.87. You see that? By changing the K, we changed the values of our poles. Now, someplace, let's draw those poles. Let's draw those poles. In the first scenario, when K is 0, we have one pole at 0. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. Okay? If the K is 0, I have one pole here and another pole here. Are we good? Now, if I change the K to the 5, I'm gonna have minus 9.47. Let's say it's here. And the next one is gonna be minus 0.53. Let's say it's here. Are we good? If the K is 10, this pole is gonna be minus, this is my first pole, is gonna be minus 8.87, so somewhere here. The other one would be minus 1.13, somewhere here. Are we good? Next one, for 20, we have minus 7.24, so somewhere here. The next is going to be minus 2.76, so somewhere here. And my last one is going to be minus 5.J3.87. Minus 5, 1, 2, 3, 4, 5. .87, a little bit lower than 4. 1, 2, 3, 4, a little bit lower than 4. So I'm gonna have holes here. Are we good? Are we good so far? Now, look at the movement. Look at the movement of my first pole. As I increase the K, moved from here. I have to do that in the actual line, but I want to see for you to see, so I'm gonna move it here. So it's actually should be on the x-axis because this is the place of those poles. Okay, so this one moved here, and then this is minus J plus. So and then it moved here. Are we good? This one moved here, and at this point, it start moving down to this point. So by changing the K, I saw that my poles are moving, and I can have the trajectory of those movements. Now, let me actually run a larger K, like 50. In 50, I have -5 plus J5 and -5 minus J5. So in 50, J5, 1, 2, 3, 4, 5, I'm gonna be further up and down for the poles. So you can see I can see the trajectory of my poles when the K is changing. Now, using your understanding over the stability that we talked about for a static system. If I have this system, which is this one, and I have a dynamic parameters, which is that K, okay? By changing that K from zero all the way to infinity, which we can see that if I increase the K, is just gonna move, first pole moving up, second pole moving down. If I change K from 0 to infinity, what happens to my poles? And if you wanted to run a stability analysis based on what you learned for a statistic system, what is your judgment over this system when we have a variable element in our system? What do you think about this system in any arbitrary value that we can have for K? Is it stable? Is it unstable? Is it marginally stable? Can you tell me? What was the definition of the unstable? In previous discussion that we had for the statistic value, there is no movement. We have solid poles. What was the definition of the unstable? What was the location that the pole can have, and we say unstable? What? Unstable.
Like the X.
X is this one. Y is this one. Where in this whole area the pole should be that we would have an unstable system? In what situation we would have increasing exponential? We are going to have an exponential, let's say AT, alpha t. What values of alpha this exponential would increase to infinity? No, t goes to infinity. Okay? If we have a positive number, when t goes to infinity, alpha t goes to infinity, e goes to infinity. It's the power of that. If we have a negative number here, alpha t goes, when t goes to infinity, alpha t goes to the minus infinity. What is the e to the power of minus infinity? 0. And if its alpha is 0, it's e to the power of 1, regardless of what t we have. So it's always going to be 1. Now, knowing that, where in this plot I could have that pole alpha and have an unstable system? Right hand side. You remember that? We said if we have a pole on the right hand side of our plot, we have an unstable system. Are we good? If we have a negative pole in the left hand side, we said it was stable. And if we had anything on the x-axis and the y-axis beside the zero doesn't count. Anything on the y-axis, any non-zero number on the y-axis as a pole, marginally stable. Now, look at this graph and tell me if this system, knowing that the k is changing from 0 to infinity, is it stable, unstable, or marginally stable? Why is it stable?
I can say.
Yes, let me kind of like restate that. Okay. By changing the k from 0 to infinity, we draw the trajectory of those poles. Regardless of what k is, the poles still remain on the left-hand side. So now that system is stable regardless of the k. Are we good? Now, if for any type of reason in any system, these poles start moving to the right-hand side, then let's say we have a system, okay, that the pole is here, and after certain values, after certain k, it start moving toward the right-hand side. It should be symmetric, so okay. That means from a certain k here, let's say it's k1, if we increase the k after that point, we are going to move toward the unstable system, the unstable region. And at k1, we have two non-zeros poles. Use this. I don't want to confuse you with zeros. Two non-zeros poles at the imaginary axis, meaning at that k1, we have marginally stable system. But before that, from k's between 0 and k1, we have a stable system. Now, knowing that, we are going to talk about that further in the future sessions. Knowing that, what would be your kind of like what strategy or what kind of like action you would take for this system to make sure we always want to stabilize, we have a stable system. We want to make sure that we have a stable system. What action in your design you have to take knowing that this is the trajectory of the poles of the system? What you should do to make sure you always have a stable system?
Make sure you bound from like bound a certain interval where it's always going to be stable.
So you should not let the k to go beyond ky. So that would be your engineering solution. Now, how to do that is depends on the system. You know, it's gonna go to the other kind of like aspect of engineering. For example, you want to bound the resistor to a specific value. Very good. You should not allow the resistor to like move forward from certain, like move up from a certain values, or the capacitor to move up from a certain values. This is actually the concept of the resonancy, this case. these K's are the concept of the resonancy. In the second order, for a certain system, when this is K is your omega n squared. If you reach a certain value of omega n natural frequency, if your input reaches the natural frequency, you have a resonance, right? So this is in parentheses. I just wanted to like give you an intuition. So this is how we can use our plot diagram and the technique that we have for root locus. We said root locus is the closed loop feedback of our transfer function. Okay, we want to analyze the stability of that. When one or two of the variables are one or two parameters in our system is variable. So we run the root locus definition over our example transfer function. Okay, solve for the poles. We saw that the poles depends on K. Okay. Look at the case, and we saw what would be the trajectory of the poles if we change the K. And based on the trajectory, we saw that, okay, we have a good system, and it's a state. Now, for some design, for example, like a bridge, okay? Like you want to build a bridge, not an electrical system. Electrical system also has the same situation. You want to build a bridge. You analyze the system and you find out, okay, in a certain environmental situation, the vibration that it gives you, the vibration applied to the bridge is like, for example, 100 hertz. Okay? And if you design your bridge where that K is going to be 10 to the power of 4, that means your natural frequency of your system is that 100 hertz. So you have a situation when you use that bridge that you can reach the resonance frequency, and you already see in the history that if you have a resonancy, that bridge would collapse. Okay? Now, what you can do, when you're designing, you put the natural frequency as a variable, and you use that to control the natural frequency when you're designing. So you make sure that in this graph, you are at a certain point with that specific design of K, you are at a certain point that you are not going to end up with the K that has a natural frequency of that 100 hertz in your performance situation. Make sense? So this analysis not only give you the ability to run a stability analysis when you have a variable in your system, but also give you the ability to design your system in a way that you can make sure that under any type of condition, under any type of forced input, you remain stable. What we have here. You want to design it in a way that never K goes over K1. So that's it for today. If you have any question, let me know. Otherwise, have a great rest of the day.